降下来。 Good. So, assignment 2, most of you should know by now, assignment 2 has been released. For this week and next week, we're going to have those extra lab sessions like we did in weeks 5 and 6. So go along through there if you want to ask some advice. Just one thing. The spec. Two things about the spec. So there was one just for part 3. There was one part where we had a function that was returning 2 values that actually should only return 1 value. So I'm just looking for the FAQ. Yes, part 3.py, there was a method that was returning batch and vocab, but we realized it should only return batch, so we just made that slight update to that file. And the other thing, I think Alex put in a note about additional libraries, but actually unfortunately we can't get the system support people to install new modules or libraries in time for this kind of thing. So you'll have to just make do with the libraries that are installed there. So whatever you do, make sure that it runs properly on the computer science CSE machines when you submit, because we can't get them to be installed system-wide, and if we installed them for one person, then someone else would complain that they didn't get access to the same library. So just keep that in mind. Good. So we talked about supervised learning, and then we talked about reinforcement learning. Now we finally get to unsupervised learning. So this week it's going to be devoted to unsupervised learning. So we talk about Hopfield networks and Boltzmann machines, and if we have time, autoencoders. And then next week we'll look at generative adversarial networks, which is the last major topic for the course. I'm not sure. It's possible next week might be the last lecture. We're allowed to have a lecture on Monday, week 11, if necessary, but we'll just see how much material we get through. Right, so we'll talk about content addressable memory, Hopfield networks, generative models, Boltzmann machine, restricted Boltzmann machine, and deep Boltzmann machine. So we start out with the Hopfield network. Now this is inspired by the ability of humans to have kind of content addressable memory. So often if you're given part of something, you can recognize the whole thing. So if we see an image, sometimes we see an object that's occluded, but we can kind of imagine what the whole object would look like if it were visible. And the start of famous phrases always sort of brings to mind the rest of the phrase, at least if you're, studied literature in an English-speaking country, to be or not to be. That is the question, a very famous line from Hamlet, and this was a phrase from Julius Caesar: I came, I saw, I conquered, right? His description of his Gallic campaigns. And so the question is, well, can we try to recreate this in computers and, content addressable memory? So if this is sort of the start of the thing, it's like something's stored in there and you're trying to retrieve it. And later on, we'll see how we could try to generalize this. Well, I want to retrieve just something similar to this. So it's easiest to think about this in terms of images. So let's say you have these 3 images on the right stored somehow in your memory. I mean, excuse me, this is a model that goes back to the 1980s. So you've got these 3 images stored in there, and then if you start with a kind of corrupted version of the image, the idea is that the network should somehow try to restore the original image, to retrieve that memory. So it could start with an image that's just kind of static, white noise, and it's an iterative process. The image sort of gradually changes to be back to the stored image, or maybe the half of it is blank and you're just given the other half and it restores it, or maybe even just a quarter of the image, if you might be able to restore it from just a quarter. Now, the way we do this is using something called an energy-based model. So the idea here is we try to define an energy function on the set of images in such a way that those specified images, for those specified images, this energy is very low. And so then if we start with a random image or a corrupted image and then try to make small changes to it, little by little, gradually reducing the energy, we should recreate the original image. So it's kind of turning around the idea of constraint satisfaction problem. So there's this sort of field of artificial intelligence called constraint satisfaction or operations research, where you specify an energy function, then you have to find a configuration that minimizes that energy function, or sometimes it's expressed as constraints. You're trying to find something that violates as few constraints as possible, or ideally no constraints. And so you count up the number of constraints that are violated and you treat that as an energy function. So this is an example. Those of you who took the AI course will recognize this is a famous constraint satisfaction problem. You want to put 8 queens on a chessboard in such a way that no 2 queens are attacking each other. And so whenever we have a pair of queens that are attacking each other, that's called a conflict. And so you start with a random, or 8, or n by n chessboard, or any size of n. And so we start with a random configuration, and we see that there's 5 cases where the queens are attacking each other. So then we pick a random. In this case, we use a bit of domain knowledge to help us with this. We say, okay, well, we know that there has to be exactly 1 queen on each column, because if there were 2 queens on the same column, they'd be attacking each other. So we pick one of the queens and we decide to move it somewhere. We randomly pick one of the queens and we want to move it somewhere on the same column, and we look at all the possible places on that column and find the one that violates the fewest constraints. So by moving that queen up the top, we remove 2 of the constraint violations, 3 of the constraint violations, only 2 left, and then if we move that queen down, we remove the other violations. This is obviously a very, very simple example, but in fact, this can be applied to much larger versions of the same problem. So here's a slightly bigger version, a normal 8 by 8 chessboard. So we randomly pick the queen on the 8th column, and then the numbers there are how many constraints are violated if the queen were moved to each of those squares, and we try to find the minimum value, and if there's 2 possibilities, we kind of pick one at random. So we've moved the queen up to the 3rd row because it was only violating 1 constraint. And then at the next time step, we randomly decide that the queen in the 6th column is going to be moved. And this is saying if we move the queen here, it would attack 3 other queens. This one, and this one. Here it would attack this, and this, and so on. But there's one placed down here, if we move that queen down here, it won't attack anyone else. So if we kind of repeat this process a sufficient number of times, eventually we may get to a state that violates no constraints. Right? So this is sometimes called hill climbing because we're, well, when we call it hill climbing, we think of it as a function that should be maximized. So we're trying to climb up to the top of the hill. But in the present context, or mostly for this course, we try to minimize something rather than maximizing it. So we turn the picture upside down and we say we want to get into this global minimum. And this, you've seen this picture before. I showed you this picture when we were discussing gradient descent. So this is very similar to gradient descent, except we don't have the gradient to tell us which direction to move in. So instead we just pick a random direction and move a little bit in that direction, right? And so you kind of like this can be likened to sort of mountain climbing in a thick fog. You can't really see anything far. You can only see something in a very small distance around you, but you can try taking one step in a few different directions and see whether that leads you downhill or not. And if you go downhill, if making this step doesn't send me downhill, I stay where I am. But if making this step sends me downhill, then I decide to take the step. So it's just this kind of random hill climbing. Yeah. Right, now, so this is kind of the normal situation where we're actually given an objective function and then we're trying to minimize it. So now we're kind of turning this around and saying, well, I'm given the solutions, and you've got to devise an energy function which will have a very low value for those particular images. So it's instead of starting with the objective function and going to the solution, we start with the solutions and then pick an energy function that will be low for those solutions. That's kind of like the twisted back way of looking at this. Okay. So how do we do that? Well, let's consider these to be black and white images. So each pixel, not even grayscale, but simply black and white. So each pixel is either completely black or completely white. This is the sort of simplest case. And so we can say that the image, let's say the number of pixels in that image is D, then a configuration or an image X is an assignment X sub j for j between 1 and D that's equal to -1 or +1. So if the pixel is black in that particular image, xj would be -1, and if it's white, it will be +1, right? So here's so these images, like the black parts are -1 and the white parts are +1. Then we can define so we're going to restrict ourselves to a quadratic energy function. So that means that we have a certain contribution. If a certain pixel location is black or white, that may have an effect on the energy. Raise it or lower it a bit by the factor bi. And then we've considered pairs of pixels, and if those two pixels are the same color or opposite colors, that has an effect. So if those two pixels are the same colour, then if pixels xi and xj are the same colour, then we subtract wij from the energy, and if they're opposite colours, we add wij to the energy. And the reason for the 1/2, right, so, well, in principle, wij could be different from wji, but normally, to ensure good behaviour of the model, we assume that it's symmetric. So wij is equal to wji, in which case the 1/2 just ends up adding two copies of this. So that's why, in that case, it would increase or decrease by wij, because it's a half of wij plus wji, which is the same as wij. And also, for the point of simplicity, we often set the bi equal to 0, so we just have this term. Now, why would we... So what is this energy function actually trying to achieve, or what does it represent? Well, the idea is this, that if wij is positive, that means that images in which those two pixels are the same will have a lower energy, right? If wij is positive, then if xi and xj are both equal to +1 or both equal to -1, then wij will be subtracted from the energy, taking us to a lower energy, right? If wij is negative, that means that images for which those two pixels have opposite colours will have lower energy, right? So this wij should be a measure of somehow the correlation between those two pixels, not in a single image, but across the set of images that we want to store. So the example I showed you, we only stored 3 images, but we could store several hundred images if we have a big enough network. Right, so we define this energy function, and as I said, we normally assume that wii is 0, and that wij equals wji, and also that bi is 0. Now you'll notice this looks very much like the weights and biases in a neural network, but it's different from the feed-forward networks that we've looked at before in a number of respects. So first of all, so we can think of these xi's as if they're neurons, and then there's this loss function we want to minimize. But in our case, these values don't vary continuously. They have to take on discrete values. So you're not allowed to have xi just change to be 0.4 or something like that. If it was previously 1, it has to either stay 1 or change to -1. It doesn't have a choice. I mean, it can't be in the middle. And secondly, the neurons are iteratively updated either synchronously or asynchronously based on the current values of the neighbouring neurons. So it's not like the feed-forward networks we looked at before. You just feed in the image and each layer calculates its activations and then something pops out the top. But here you've got a kind of iterative process where the things are changing continually over a period of time. Okay, so the way it works is this. Let's say once the energy function is fixed, we start with initial state x, and then we repeatedly try to flip the neuron activations one at a time in order to get to a lower energy state. So we pick a particular, we have an image and we pick a particular pixel, xi, and then we have to decide on whether to keep the current value or whether to switch to a new value. So you look at that energy function and you say, well, if I were to change to the other value, would my energy go up or would it go down? If the energy will go down, then you make the change. But if the energy either stays the same or goes up, then you don't make the change, you stay with your current value. So if you look at that energy function, you try to figure out what will be the change if xi change, if xi changes, then the factor that xi is multiplied by is this, sum over j of wij xj plus bi, right? So you figure out that value, and then if that number is with the current values of all the other pixels, and because I'm only in this model, I'm only allowed to consider changing one pixel at a time. So I just think, okay, if the whole rest of the image all stayed the same and only this one pixel changed, will that increase the energy or decrease it? So if that value there is bigger than 0, that means the energy will go down. So that means that the energy will become lower if xi changes to +1. So I change to +1. If that value is less than 0, that means the energy will be lower if xi goes to -1. So I change it to -1. And the way this algorithm works, if the value is 0, that means that the energy wouldn't change, but what I do is I just keep the value that I currently have. So if it was +1, I keep it as +1. If it was -1, I keep it as -1. So this kind of creates a stable state, or makes the network behavior more stable. So I don't change. I stay where I am unless changing will get me a strictly lower energy. And it turns out that if you follow these rules, clearly if you follow these rules, the energy will never increase. It will only ever stay the same or decrease. And eventually it must reach a local minimum, because eventually it must reach a point. The algorithm will only stop if it reaches a point where, there's only a finite number of configurations. The number of configurations are very large but finite. And eventually the algorithm must reach a point where if any one pixel were to change, the energy would increase, right? So that will be a local minimum. Okay, so how do we, if we're given a set of images, how do we come up with these wij's? Well, so it simplifies things if we just set bi to 0. We're not going to have any bias. We're only going to look at the interaction terms. And the trick is, as I said, it's kind of like the correlation. We set we set wij equal to 1 over d times the sum from k equals 1 to p of xi k xj k. So but now notice p is the number of images being stored, and D is the number of pixels in the image, right? Or D, that's right. The D, if it doesn't have to be an image, it could be D is just the number of neurons, and P is the number of patterns, but it's easiest for us to think about it as images. And you take the sum for k equals 1 to p of xi k times xj k. Remember, these numbers are either 0 or 1. So either 1 or minus 1. So when we multiply them together, we get a number that's either 1 or minus 1. And so, in other words, the weight is based on the fraction of training items for which the 2 pixels are equal. It's not quite equal to the fraction because we don't want a number between 0 and 1, we want a number between minus 1 and 1. So we take the fraction of images for which those 2 pixels have the same colour, and we take minus 1 plus 2 times that value, and then we multiply by this P over D, which is this turns out to be, just give a nice result mathematically, we multiply by the number of patterns and divide by the number of pixels, the number of neurons. And so that gives us, in other words, if those 2 pixels have the same colour in half of the images and opposite colour in the other half, then this weight would be 0. If the 2 pixels have the same colour in more images than they have opposite colour, then this weight will be positive. And if they have opposite colour more likely than the same colour, then this weight will be negative. Right. So again, you can go back to these images. You can sort of see, if you consider, let's say you consider this pixel and this pixel, or this pixel and this pixel. This pixel is white and that's black. Here that's white and that's black. Here they're both black, right? So two times out of 3, these 2 pixels have opposite colour. So that there would be a negative weight assigned to that pair of pixels. So you're assigning a weight for every pair of pixels. Now, this is also related to the concept of Hebbian learning. We talked about Hebbian learning in the first lecture. Hebbian learning is a process where if one neuron fires and then another neuron fires at the same time or shortly afterwards, the connection between those 2 neurons increases. This is a kind of similar situation that you have one neuron for this pixel and one neuron for that pixel, and then if they're the same colour at the same time, that's analogous to the idea of both of them firing. It's a sort of loose analogy, but it makes some sense. And interestingly, one consequence of this is that if a certain image is a stable point, if you go through this process and you get to an image that's a local minimum in the energy, that's called a stable attractor. And one consequence of this particular formalism is that if a particular image is a stable attractor, the negative of that image is also a stable attractor. So if I took these images and replaced them, just changed every black to white and white to black, I'd get the negative of the image, and the negative image of the image could also be retrieved. Now, you can do some mathematics and statistics to figure out how likely it is that the images will be stable. So the thing is, you can store a certain number of images reliably in this network based on the number of neurons. So it's kind of, it's this ratio of the number of images, this ratio of the number of stored patterns compared to the number of neurons is important. So depending on how many neurons you have, there's a certain number of images that you can store, and you can be confident that those images will be retrieved successfully. But if you try to store a larger number of images in there, then things will go wrong. So you won't retrieve exact images, but you may get some sort of weird mixture between two images. So you get this kind of degradation, spin, what physicists call spin glass states, and so on. So we won't go through all the mathematics, but basically it works out like this. If you plug, the sum, if you plug this into here, if you figure out what this is, sum over j of wij xj based on this, you get this kind of double summation. So this is the number that tells you whether or not a particular pixel is going to flip or not. And if you plug in the value for wij, you get this double summation, and then you can you can rearrange it into this. So xil. So this term is the one that you want. So this is this is what we calculate, and depending on whether this is positive or negative, it'll tell us whether the next value of xi L is +1 or -1. And it turns out that because this value is calculated based on comparing the signs of the other pixels with xi, this turns out to be equal to xi plus this extra term. So if this combined term is positive, then the next value of xil will be +1, and if this whole thing is negative, the next value of this will be -1. And so you can see if this term here is, this term here is the current value of xi, so this term here is called the crosstalk term because it's the term that could potentially get us to change erroneously. But if that term is, if the size of that term is less than 1, if the absolute value of that term is less than 1, then it won't affect the sign, right? So if this is +1 and then the absolute value of this is less than 1, then the combination has to be positive. And similarly, if this is -1 and that's less than 1 in absolute value, then the combination has to be negative. And right, that's basically what the analysis is based on. It could turn out that this is bigger than, that this, if you're lucky, even though this value could be bigger than 1, but if it's positive, and this value could be bigger than 1 in absolute value, but if it happens to be the same sign as this, then again, this will be preserved. So the real question, but the question is how likely is it that this value will be bigger than 1? And this is, as I said, we won't go through all the statistics in detail, but this is, you think of this, you imagine that these numbers are independent, then it's like if you toss a coin several times, what's the likelihood that the let's say you toss a coin p times, and if you get +1, if you get a heads you add 1, and if you get a tail you subtract 1, then on average you expect they'll cancel each other out and you'll get back to 0, but then there's a certain probability that you'll get that the number of heads will exceed the number of tails by d, right? So this is what it comes down to. You toss a coin p times, what's the likelihood that you get d more heads than tails, or d more tails than heads? And if we can assume that this is if we assume that these things are independent and you get like a normal distribution, then you can figure out that probability, right? And that's where we get this magic number of p over d less than 0.138. So if that ratio is less than 0.138, we can expect the patterns to be stored and retrieved successfully. If we try to store more patterns, then we may get sort of spurious stable states emerging. I know this is a little bit abstract, but let me just... maybe I can just... There will be an exercise dedicated to this. If you work through the exercise, I think you'll have a better understanding of what's going on. But let's just think about a very simple example. Let's suppose I have 4 neurons. Let's suppose one image looks like this, +1, -1, -1, +1, and another image is -1, +1, +1, -1, then, well, and this is +1, +1, +1, +1, then you can start to see, if I try to make a network out of these, well, the weight here, these are opposite, and the same, so this value would be negative. Here we've got the same, opposite, same, so this weight would be positive, and we kind of go through like that. These are more likely to be the same, these are more likely to be negative, these are more likely to be the same, and these are more likely to be the same. So you kind of get the idea what these weights look like. And let's say we had this is neuron 1, 2, 3, and 4. If I try to write this W matrix, let's say I have -1 and -1, this would mean that these two neurons are likely to be opposite to each other. And then if I had like +1 here and +1 here, that would mean these two things are likely to be equal to each other. You know, this is a very simple example. Let's say everything else is 0. Well, then an example of a stable state for this weight matrix would be plus 1, plus 1, plus 1, minus 1. This would be stable because these two things are the same and these two things are opposite. Another example would be minus 1, plus 1, plus 1, plus 1. Right, so again, these two are opposite and these two are the same. And to test whether a state is actually stable, let's say we take this state here and test whether this is stable, well, we have to multiply this weight matrix by this vector and see what the new vector is. So here we say, okay, if we do this as a matrix multiplication, this is 0, 0, 0, minus 1 times minus 1 is plus 1, 0, 0, plus 1 times plus 1 is plus 1, 0, plus 1 times plus 1 is plus 1, and minus 1 times plus 1 is minus 1. So, because this is the same as this, that means it's a stable state. Okay. And if you've got a 0 here, it would also be a stable state because of this rule that if the change in energy is 0, then you stay where you are. Okay. So that's quite a simple example, but if you try to work through the one that I'll post on the exercises, you'll see something a little bit more sophisticated. Okay, any questions about this? Yes? Yes. Sorry, say it again.
So the neurons in the second image which you do.
The neurons.
So do they correspond to an image or do they correspond to individual pixels?
Yeah, the question was, do they correspond to an image or do they correspond to an individual pixel? Right, so yeah, this notation, this xi, so the little I underneath corresponds to a pixel. And the k in the brackets above corresponds to an image. So what this is saying is I look at image xk and I look at the ith pixel, and then I look at the same image and look at the jth pixel, and I see whether I multiply them together, so I get either plus 1 or minus 1, and then I sum these values up over all the images. Right, so this expression here is the number of it kind of counts the number of images for which those two pixels are the same, and then subtracts off the number of images for which they're different. Yeah. So so the higher subscript in brackets is the image, and this one is the pixel.
So how would you calculate the value for D?
Well, D is the number of pixels, so it's specified in advance.
D is the number of neurons and the number of pixels.
Sorry, no, good question. I'm glad you asked this. This is a little bit confusing. So this is not an average. This is not a straight average. P is the number of images, and D is the number of pixels. D is the number of patterns, and P is the number of neurons. So I'm adding up P things, but then I'm dividing by D. So it turns out mathematically that this scaling gives you some nice properties. But the number of things I'm adding up is the number of images, but the thing I'm dividing by is the number of pixels. So it's a little bit unusual in that respect, but for some reason this gives the best result because it gives you something that's likely to store the most patterns stably.
So what you measure as number of pixels and number of neurons are the same?
They're not the same. No, we don't assume that they're the same. They're different numbers. We normally assume that they're in this kind of ratio. However many pixels we've got, if we've got 100 pixels, then we can store, if we've got 1,000, if we've got 1,000 pixels, then we can store, this is a good way to think of it. If we've got 1,000 pixels, we can reliably store 138 images. So if the images are 32 by 32, which like the MNIST images, that's about 1,000 pixels, and then the number of patterns we normally would try to store in there is 138. If we try to store 138 images, it'll probably be successful. If we try to squeeze more images in there, it will fail. Okay, now, so this Hopfield model, like I said, is very early. It's a very early model, and it was just meant to store and retrieve images. So we store a certain finite set of images, and we're trying to just reconstruct exactly those images. So it's kind of like you think of it as, trying to remember exactly things that happened in the past. But often what we would prefer to do is actually generate new images. So this is much more exciting, much more kind of modern, is the idea that you give a certain set of images to the network, and then you ask the network to produce new images which aren't quite the same as the ones you gave, but are sort of in a similar style, right? So we're going to look at a few different ways to do this. First, the first one we're going to look at is called the Boltzmann machine, which is similar to the Hopfield network, but a little bit different. The second method we're going to look at is called the autoencoder. And then next week we'll move on to the generative adversarial network. So almost the whole rest of this course is going to be based on generative models. So the first one is the Boltzmann machine. Now, I just actually, maybe to make this a bit more tangible, let me just try to, I was looking for some videos of this. Because it kind of shows you more what makes the thing a bit more tangible. Let me see if I can find this. Okay, let's look at this one to start with. So this is and again, this is sort of older work now. This is from the early 2000s. But this was sort of from Jeff Hinton's lab. This is a network. It's fed these MNIST images, these digits from the Canadian Postal Service that we looked at before in terms of classification, but the system here is trying to after looking at all of these digits, it's trying to make up sort of phantom digits, right? So it's, again, like it's not, it's a fairly simple kind of data by modern standards, but you kind of get the idea of what's going on. And these things that it sort of like imagines these phantom digits, and most of them do kind of look pretty much like realistic digits. But here you see the nature of a digit will change. So if you look, keep your eye on the digit in the middle and the top row, it starts out looking like a 3 and then sort of gradually morphs and maybe looks a bit like a 5 and then a 6 and then an 8 and then a 6 again. So these things kind of shift around, and eventually if it ran, the idea is if it ran for long enough, it would sort of eventually go through all different types of digit and all the 10 different digits and different sort of styles of each digit. Okay, so how does this work? Well, okay, it's very similar to the Hopfield network. In fact, the energy function looks exactly the same as for the Hopfield network. The formula looks exactly the same. We have these weights Wij, and we assume that Wij and Wji are equal, so instead of having the full sum with a half, we just sum over I less than j. Without the half, it gives us the same answer. So the form of the equation is exactly the same, but now instead of taking on the values of -1 and 1, we instead take on values of 0 and 1. This turns out to be a more kind of general model, and if you remember the Hopfield network, one of the consequences of this -1 and 1 was that if you stored one image, the negative of the image would also be stored. We kind of don't want that. We don't really want that symmetry. So this kind of gets rid of that. So these xi's are either 0 or 1. And as I said, the purpose of this is to generate new states rather than retrieving old ones. And the update is not deterministic. It's stochastic using the sigmoid function. Now, in order to explain the motivation of this, I have to tell you a little bit about this. Has its roots in physics and what's called the Ising model of ferromagnetism. Okay, so if you take an iron bar, you can magnetize an iron bar and turn it into a magnet, right? So you can have an iron bar that isn't a magnet and one that is a magnet. And the way if you've got an iron bar and you want to turn it into a magnet, normally you heat it up to a high temperature and then you cool it very, very slowly in a magnetic field. And if you cool it slowly enough, it will become a magnet. And that process is known as annealing. The word annealing means to cool something down slowly. And if you look at the actual physics of this, inside the iron magnet there's all these little ions, and each one has a spin, and the spin is either up or down. So because of quantum effects, we get this discretization. The spin has to be up or down. It can't be in the middle somewhere. And these little guys are flipping their spin all the time from up to down, but they prefer to align themselves with the spin of their neighbours, right? So every time, if this guy, this guy is someone who's very likely to flip because all of his neighbours are up And so if he manages to go up, he'll achieve a lower energy state. And in fact, the energy function looks very similar to this, or it's actually exactly the same as this, but each ion only interacts with its neighbours, not with all the other ions. So Wij is, if this is I and that's J, then Wij will be 0. You don't interact with anyone who's far away. But if Wi and Wj are next to each other, then the energy gets increased by 1 if those two neighbours have their spin pointing in the same direction. Sorry, it gets decreased, but the energy gets decreased if they're pointing in the same direction, because we want the energy to be low, but if they're in opposite directions, the energy gets increased. And what's actually going on when that thing is cooling down is the following. Whenever if you assign if you assign, this is the same phenomenon we were just talking about. An image here is like an assignment of +1 or -1 to all of those little ions, and we can calculate an energy state for that configuration, and the probability of it defines this probability distribution. The probability of being in that state is equal to this, e to the minus the energy of x divided by temperature, which is proportional to this, and then there's some normalizing constant. So z is just like z is the sum over all of these things. So we don't often know what z is, but this just has to be a probability. Now, you may recognize this is very similar to the softmax distribution that we talked about with classification. So when we had softmax, we had the outputs from the network, and the probability was equal to e to the plus. With the softmax, a higher output meant a higher probability. So the output the output there is meant to be the negative of the energy. A higher output is better. So the output is the negative of the energy, and there's always this kind of funny minus sign. When Paul Smolensky first introduced this model in the late 80s, he had this word harmony, which was the negative of energy, and the network was trying to maximize harmony, but I think he called the model the harmonium, but it got too confusing to have these extra words, so we just try to remember that it's the negative of the energy. And so let me just show you I'll show you a video of the icing model again so that you can have an idea what's going on here. So all right, this is this equation. So you started with a random state, and these guys are flipping. So the blue ones are like spin up, and the white ones are spin down. And the lowest energy state, there's is either everything is all up or everything's all down, but it takes a long time to eventually get into that state. So randomly, what's happening here is randomly each guy is, you pick a random pixel here, you look at the 4 neighboring pixels, and the probability of the thing becoming blue or white is based on how many of the neighbours are blue or white. So if 2 neighbours are blue and 2 are white, then you'll have an equal chance of either colour. But if like 3 neighbours are blue and 1 is white, then you're more likely to become blue. And if more neighbours are white, then you're more likely to become white. So it changes the probability, but it doesn't like absolutely guarantee you're going to change to. You're more likely to change to be equal to your neighbours, but you're not guaranteed to be equal to become equal to your neighbours. And you see gradually what happens is little isolated points of one colour tend to kind of disappear over time, although occasionally they will appear and randomly appear by random and later disappear. But over time, this sort of structure emerges. It's like a battle between the ones pointing up and pointing down, and it takes quite a long time for one of them to win out against the other. These things gradually kind of agglomerate into bigger and bigger blobs, but eventually the smaller blobs will disappear. You see that smaller blob just gradually gets wiped out. And normally it happens in 3 dimensions, of course, but the same kind of thing can be observed here in 2 dimensions. Okay, so what are the actual equations that are happening here? So if you just pick one pixel and try to... Okay, so the idea is that you just pick one pixel and decide whether to change that pixel. Right, so you consider that the thing is in a certain state and a particular component is equal to 1, and then it has to decide whether to change to 0 or not. So remember, we're with the Boltzmann machine, the possible values are 1 and 0. Now, so let's say the original state is, the energy of the original state is E of x, and then if you change from 1 to 0, the new energy will become E of x prime. So then the probability, it's hard to compute the overall probability, but really all we need to know is the difference in how much is the probability going to change with this flip. So if the change in energy is if the old state was E of x and the new state is E of x prime, then the probability of the new state must be equal to the probability of the old state multiplied by e to the minus delta E over t. Right? That's a consequence because everything else will stay the same in this expression. It's just going to be the E of x is just changed by delta t, so that means that the probability, when we change from x to x prime, E of x will be replaced by E of x prime. So this term here will get increased by delta t, and that means that the probability will get multiplied by e to the minus delta t over the temperature. sorry. Right, so the new probability will be the old probability multiplied by this factor. And so if we just want to know if everything else is fixed, what's going to be the probability of that particular neuron being 0 or 1, well, the probability of it, this is like a conditional probability, it's conditioned on everything else staying the same, then the probability of it being 1 must be p of x divided by p of x plus p of x prime. Because remember, x and x prime are identical except for that one neuron changing. So the conditional probability of it being 1 based on everything else staying the same must be p of x divided by p of x plus p of x prime. And this is equal to 1 over 1 plus e to the minus delta e over t, right? So that's the probability that it will stay in equal to 1, and the probability of it switching to 0 must be 1 minus that, which is this value here. And again, I know there's quite a lot of equations, but I kind of like this because it draws together a lot of the previous ideas from the course. So we've talked previously about the sigmoid function. This actually shows you how this sigmoid, this is actually the sigmoid function of applied to delta E over T, right? So this shows you kind of naturally how the sigmoid function arises. Okay, so the Boltzmann machine operates similarly to the Hopfield network, except that there's some randomness in the updates, right? So if you think back to the Hopfield network, in both cases we repeatedly choose one neuron and decide whether to flip it or not, right? So we start with a configuration, we pick a neuron and decide whether to flip it, or we pick another neuron and decide whether to flip it, and we just keep repeating that process. But the difference is this, so with the Hopfield network, we calculated the change of energy, and we never move to a higher energy state. You know, we pick a neuron and we say, okay, well, if flipping that neuron will get us to a lower energy state, then we'll do it, otherwise we won't. So it was a deterministic process. Now, the way the Hopfield network works, the Hopfield network, right, so this delta E, so I'm using delta E to be the difference between the energy when x is 0 and the energy when x is 1. So if delta E is less than 0, then we're allowed to switch from 1 to 0, and if delta E is bigger than 0, we're allowed to switch from 0 to 1. But otherwise we have to stay where we are. Now, with the Boltzmann machine, we choose the value, we go to the value xi equals 1 probabilistically, right? So if the change in energy, if delta E is 0, then e to the minus 0 is 1, so we get 1 over 1 plus 1, which is a half, right? So if the two states have the same energy, then with probability 1/2, we switch, right? Because we don't care. If delta E is negative, if delta E is positive, then this is a number less than 1, so P will be bigger than 1, right? So we're more likely to, if delta E is positive, we're more likely to switch to x equals 1, because delta E is the energy, delta E is the additional energy for the 0 state. It can't be greater than, it's not greater than 1, but it'll be greater than a half. Yeah, P is always between 0 and 1, that's right. So if delta E is positive, then we're more likely to choose 1, and if delta E is negative, we're more likely to choose 0. But it's not guaranteed. There's always some randomness. And it's also can be modulated by the temperature. Right, okay. So, right, so if we repeat this process many, many times, eventually what we're going to get is something that's sampled from the Boltzmann distribution. Okay, so T, right, so again, if the temperature goes to infinity, then we get 1 over 1 plus e to the minus 0, which is a half. So if the temperature is infinity, we've always got an equal chance of choosing 0 and 1. So we just end up with a uniform distribution. As T approaches 0, the behavior becomes similar to the Hopfield network because we always change to the lower energy state. Now, this is a little bit confusing, the terminology, but sometimes we vary T. So sometimes we keep T fixed. If we keep T fixed, technically speaking, it's not really annealing at all. It should be called the metropolis algorithm. But there are some situations where we start with a high temperature and gradually decrease the temperature, and that's when it really gets called simulated annealing. So the sometimes we use the term annealing at fixed temperature, but that phrase doesn't really technically make sense, but that's what people do sometimes call it. And just, I know we're going to take a break soon. Let me just sort of say what's going on here. So the problem with the Hopfield, if the updates were deterministic, we could get stuck in a local minimum, which is what we don't want. So the idea here is, when the temperature's, you start with the temperature high and you're just sort of wandering randomly all over the place. As you decrease the temperature, you're sort of still wandering, but you're spending more time in the regions of lower energy. And the idea with the annealing, if you anneal too fast, you may still get stuck in a local minimum, but if you anneal slowly enough, you should end up down in the global minimum, right? So I didn't, in that video, I don't have a corresponding video, but you can, it turns out like if you were to run the simulation and only allow movement to a lower energy state, it would converge to a local minimum. You would get little tiny blue blobs and little tiny white blobs, and then it would get stuck and wouldn't get to the global minimum. So we have to add in that randomness in order to get us to that local minimum. Okay. Any questions about this? Okay, let's take a 10-minute break, and then we'll continue the discussion.
I was actually confused with understand like what P and D are? Like, first of all, like, initially it was used as number of patterns, and then it is somewhere mentioned as number of pixels too.
Where does it say, maybe there's a mistake here, where does it say it's the number of pixels?
Like k equal to 1 to P, you call P as like the number of pixels.
It should be the number of patterns. Your D should be the number of pixels.
Number of pixels and number of neurons are the same.
That's right, yeah. We think of a pixel as a neuron.
So, could you explain this? This is because it's so quick.
Yeah.
On the first page. Yes, here. So here.
Well, here,
You have 3 images.
yeah, we have 3 images and 4. So P equals 3.
Yes, D equals
D equals 4.
1, 2, 3.
It will be 4 into 3 equal to 12.
There were 3 patterns here.
P
Okay.
I understand, but I thought D equal to
D is the number of neurons. There are 4 neurons.
so it is the number of pixels per image, not the total number of pixels.
Per image.
Per image, that's right. Because we think of this as yes, per image. Yeah. Sorry, I should have said the pixel per image.
If I have like the size of an image.
Yes, so data was okay. So this is 4.
Yeah.
And how do you
This is
Right.
different. It's negative 4.
So this is where
So this is the both 2 negative, 1 positive. So
that's right. So when it says positive, so yeah, so
That means we use stop. So we just some mid result.
that's right. So it's D times right. So this thing here,
Yeah.
it would be 1 over D times. So if you look at this thing here, so it's 1 over D times minus 1 plus 1 plus 1, which is 1 over D, which is a quarter. Yeah, so every time you see plus, this is actually a quarter, and this is a minus a quarter.
Can you just tell me how we got this minus and plus?
Well, these two here, so in this pattern, these two are negative, these two are opposite sides. This time this is minus 1. Here it's minus 1, and here it's plus 1.
Here it's the same, here it's the opposite.
That's
Here
right.
it's the opposite.
Yes.
So
You put them together.
So we get minus 1 plus 1 is minus 1.
Use that formula.
Using that formula.
Yeah. And the second question is in here. We have the initial weight.
Yeah,
Use this formula.
that's
Yeah.
right.
So in here, so if D is like in here, D is 1, 2, 3, 4,
Yes, right.
and P is just 1.
Right, so that's a
Yeah,
good
so-
question. So here, right, so
So that which matrix?
yeah, there should be a weighting factor out the front.
Yeah.
Right, so they're 1/2 or something.
Yeah. So, and we just compare the two. Yeah, the 1 and 4. If there is opposite, yeah, so the value is minus 1. Yeah.
That's right.
So you here is negative and times the factor.
from here to here, how do you move it? From here to this?
Oh, this is a different
Different
example.
size,
Yeah.
Yes.
different example, different size. It's just illustrating
Okay,
how
so this is just one
Mhm.
pic. And how did you come up with this? From here to here?
Right. Well, let's say we have these two patterns. So in this pattern is 1, 1, 1, minus 1, and here's minus 1, 1, 1, 1.
That is single one image. This
Well,
whole
let's
thing
say
is
there's
one
2
image.
images. Let's say this is 1 image and this is an image.
Yeah.
So then, if we look to get W, this is 1, 2, 3, and 4, right? So W1, 2, you say this times this is 1, and this time this is -1. Because in this pattern they're the same, in this pattern they're different. Times something, so that's going to be 0. But let's say we look at W2, 3. Well, they're the same here and then the same here, so we get 1 plus 1. But then we have to divide by the number of neurons, which is 4. So this will be 2 over 4, which is 1/2.
Just this.
Number of neurons, okay. But so that'll again be like just one row, right? How do you get 4 rows here? So this would correspond to one row. Like this do 1, this do 1, this do.
Because the new row is 4 times 4.
It's an interaction
It's just
between.
trying to match the size of the matrices.
Yeah, it's like this determines the number of rows and the number of columns in the
Yeah,
matrix.
you can also like flatten it and do component wise.
But it's a symmetric matrix.
So we are actually comparing these two,
Yeah.
gives the first one. Then these two and these two gives the second. Are we also doing this and this?
That's right. That would go in the row 1 and column 3.
Yeah.
Is it like it's 2 examples?
Yeah.
These are 2 examples, and if you multiply it into this matrix and you get the same result.
Outcome 0 is 0.
That's right.
In this network, we know to just update the weight.
That's right.
And we just flip that neuron. Actually, or not actually. So, what's this network actually represent? Yeah, I understand the calculation.
It just stores the pattern.
Yes,
Then if you start with something random, it will eventually probably converge to one of these patterns.
One of these patterns.
Or the negative.
Make it stable.
That's right.
So you maybe draw some image of pattern and you want to that the energy is minimal.
That's right.
Makes so the image will show you some certain
That's right.
But the weight we initial this weight and this weight is not changing.
That's right. So there's 2 processes. So the first process is you take the patterns and make the weights, and then the second process is you take the weights and try to recover.
Iteration to find the stable state.
That's right.
That makes sense.
Do a component wise multiplication of this 2. They're the same.
So we change that just follow this rule to change one new row to change or plus or 0 or not change all.
That's right.
I'm still not getting it. So if I have like 2 images, 1, 2, 3, 4, 1, 2, 3, how do you come up with this and not this? It would be like this and this together and this together. That will be element 1.
That's right.
And
1, 1 or 1, 2. That'll be element 1, 2. And then you look at this and this and this and this will be element 1, 3. And then if you look at this and this and this and this will be 2, 3.
so it is symmetric matrix.
It is symmetric. That's exactly right.
So what's the point of calculating 1, 1? 1, 1 has no meaning at all.
That's right. We don't calculate 1, 1. We just calculate 1, 2, 1, 3, 1, 4.
So the diagonal has no meaning.
The diagonal is all zeros.
And when we are converting this into a neuron structure, what are we doing in the process, like intuitively? Like when you say we are converting this image and we are like corresponding. So
Well,
what
you
does
could
this mean?
think of it as a neural network, but it doesn't have a hidden layer, it's only got an input layer. But then it has these weights
So it's just
These could be thought of as neurons, and these can be weights connecting the neurons.
so it's like corresponding to say p pixels. You would have just n neurons in one layer without any output layer.
That's right. Yeah.
So where do the weights go?
Well, the weights are within that layer. It's like fully connected within that layer.
Okay, something like a recurrence network.
That's right.
Like you finally get an image of the weights. Finally get an image of the weights.
That's right. Yeah. You just keep updating until it stabilizes.
Okay, there is no output layer. It's just one layer.
That's right.
Yeah, that is what I was in.
Is it?
What do you do with that final weight image? Just what do you do with it? How do you use it to like reconstruct?
When you start with a random image or a partial image, and then you keep updating the pixels according to the energy. Yeah.
And the final value would be the updated, like the
Stored image.
yeah, the new image.
Okay.
It's not. Oh, did I? Because the Boltzmann machine is in there. It doesn't. The book doesn't mention the Hopfield network, but I like to present it because I think it's a good way to help you understand the Boltzmann machine. Yeah.
Is there some specific book or something which you like refer for the slides?
For the Hopfield.
Yeah. Or randomly,
I
like
will
it should
try
be.
to. Oh, that's a good question. I'll try to find a reference. Maybe I didn't have a reference here. Okay, I will try to have a look for a reference for this Hopfield network.
About this part, like where's the B?
Well, if we have B, then this will be the update. But normally we set B to 0. Normally we don't have any bias. Well, for the Hopfield network, we can have it, but when we're given the images, we often choose to have B be 0. But for the Boltzmann machine, we usually do have a bias.
So it's like about stable character. I don't have to reverse
Yeah, if B is non-zero, then this wouldn't be true. I should have mentioned that, but one consequence of this choice would be Wij. So in the general model, we can have B non-zero, but if we choose B to be 0 and we choose Wij to be opposite to Wji, then it will have this consequence.
So, last question. So, thanks for so when to zero? This property near to 0.
T is near 0. Dividing by 0 is the same as multiplying by infinity. So if you have e to the minus infinity, you have e to the minus infinity. Yeah, if you go 1 over 1 plus infinity, then that's 0.
Yeah, 0.
If delta e is negative infinity,
it's equal to so the minus the
right, and in the other case it would be equal to 0.
So that means when you now is 0. And now is the energy is that you want to minimum that the xi is 0, so it's 0. So it's not affect something. If you change 1, it might be to the decrease. And if you xi is equal to 1, and then you now change to 0. Yeah, because you change to 0, you might be increase the energy. You prevent. Yeah, I think.
Depends on the, if it's plus infinity, the thing goes to 1, if it's minus infinity, it goes to 0.
Okay, thank you.
Good. Well, some. Some people were asking some good questions during the break about this example, so I just might go back just to revisit this a little bit. So because it's a little bit quick, so what I was intending here is that there are 4 neurons, 1, 2, 3, and 4, and let's say we have just 2 patterns stored in there. So one pattern is +1, +1, +1, -1, and the other pattern is -1, +1, +1, +1. So in this case, D, which is the number of neurons, is 4, and P, which is the number of patterns, is 2. And so if we want to calculate this matrix, if we look at, if we want to calculate W12, we look at neurons 1 and 2 in each pattern. So here, +1 times +1 is +1, and here +1 times -1 is -1, so we get 1 minus 1, which is 0. If we look at W23, we get +1 times +1 and +1 times +1. So we get 1 plus 1, but if you look at that formula, we have to divide by the number of neurons, which is 4. So technically it's 1 plus 1 divided by 4, which is a half. So the weight matrix would really look like this. It's -1/2, +1/2, +1/2, and -1/2. But when we calculate whether the pattern is stable or not, this scaling of a half doesn't actually influence it too much, because it's really just a question of whether the thing is positive or negative. Yeah? Now, this other example was meant to be that there are still 4 neurons, but here there are 3 patterns. So D is still 4, but P is now 3. And if we calculate, for example, the weight connecting this neuron with this neuron, here we get -1, +1, and +1. So we get -1, +1, +1, and then we have to divide by D, which is 4. So here we get 1/4. So if you were to write this as a matrix, all of these positive terms would be +1/4, and the negative terms would be -1/4. So we can write it as a matrix, but if we draw it like this, it starts to look a little bit like a neural network. So, but this neural network is a bit different from the networks we looked at before, because there's no hidden or output layer. There's really only an input layer, and the weights actually connect the neurons within that input layer, and it's like fully connected. So the way this operates, thinking about it as a neural network, we put the original value, we start with some initial values, and then we go through and randomly update different neurons. So we pick a neuron at random, we calculate the weights we do this sort of summation of the other inputs multiplied by the weights, and depending on the value depending on that summation, we decide on the next value of this neuron. So if it's a Hopfield network, if the sum is positive, then we switch our value to +1, and if the sum is negative, we switch the value to -1. If it's a Boltzmann machine, we calculate a probability based on that weighted sum, and based on that probability, we take the sigmoid of the weighted sum, and the sigmoid of the weighted sum tells us the probability of this thing being 1, and 1 minus that will be the probability of it going to 0. Okay, so this is how we think of this as a neural network. Now, having said that, this produces reasonable results, but it takes a long time to converge, because this is the original Boltzmann machine here. Oh, well, sorry. Oh, well, there are two ways in which we can modify this. So the first is we can add additional neurons. So the neurons that we've started with are the input neurons, and then I could imagine that there's certain hidden neurons which aren't part of the image but are just kind of part of the model, and then I get this kind of Boltzmann machine with hidden units. But the problem is it takes a long time for this thing to converge, or it takes a long time to train a network like this because it's like fully connected and everything kind of depends on everything else. So then we get to the notion of a restricted Boltzmann machine where we have visible units and then we have hidden units, and the visible units are connected to the hidden units and vice versa, or by symmetric connections, but the input units are not connected to each other and the hidden units are not connected to each other, and this is called a restricted Boltzmann machine. So it's sort of been extended in one way but restricted in another. So it's extended in the sense that we've added the hidden nodes, but it's restricted in the sense that the hidden nodes are not connected to each other and the input nodes are not connected to each other. We only allow connections between the input and the hidden nodes. So this transition may, if you weren't familiar with other types of neural networks, this transition may look a bit unusual, but because of what we've learned so far in the course, one way to sort of think about a possible motivation for this is just that it makes it look more like what we expect from a neural network. It's a network that has a hidden input layer and a hidden layer. So we're used to seeing networks with an input layer, a hidden layer, and an output layer. This doesn't have an output layer, but it's got an input layer and it's got a hidden layer, and the connections go from the input to the hidden layer. So in some ways it looks more like what we expect of a neural network, but the training is actually the same as the Boltzmann machine, just with these restrictions. So when we update the weights, when we update the activations, we update the hidden nodes as well as the input nodes. But the great advantage of restricting to only these nodes is that when we can update all the hidden nodes independently, because the probability, if we think of a certain hidden node and we're trying to decide whether this node should switch between 0 and 1, we don't need to consider the value of the other hidden nodes, we only need to consider the input nodes. And the same thing, if an input node wants to switch from 0 to 1 or 1 to 0, we only need to it only interacts with the hidden nodes, not directly with the other input nodes. So that probability will only depend on the hidden nodes. So this allows us to kind of compute, to parallelize this process of update. We're not restricted now, or with the original Boltzmann machine, we had to just sort of update one neuron at a time. Here, we can fix the hidden nodes and update. We can fix the input nodes and update all the hidden nodes at once, and then we can fix the hidden nodes and update all the input nodes at once. So this is actually the way a restricted Boltzmann machine is trained, is like back and forth. You change the input, and then you change the hidden, and then you change the input, and then you change the hidden. Okay, so let's just look at how these equations get slightly altered. Right, so the inputs, again, are binary vectors. They're either 0 or 1, nothing in between. It's a two-layer bidirectional network. We have the visible layer V and the input, the hidden layer H. There's no connections visible to visible and no connections hidden to hidden. There's only connections hidden to visible. And this, the energy function turns into this, right? Because the only weights that are non-zero are the ones between a visible unit and a hidden unit. So we can write, if we index the visible units by I and the hidden units by J, then we can treat this weight as Wij. And we do allow bias units, right? So with the Hopfield network, we're allowed to have bias units, but we often set them to 0. With the Boltzmann machine, we normally have non-zero bias units. And this, again, is very familiar to us, that they look like the bias units in a normal neural network. So this is the energy function here. There's one term that comes only from the visible units, one from only the hidden units, and one from the interaction between them. This energy function determines a Boltzmann distribution, and the idea is that the distribution should be, that energy function should be, if I give you a set of images, the energy function should be low for those images, and then by generalization it'll be low for certain other images as well. So this is why the network is able to produce new images, not just the ones that it was trained on. And it's trained to try to maximize the log probability of the given data. Okay. So this is a bit of terminology. I've taken this directly from the textbook. It looks a little bit, some of this notation looks a little bit unusual, but let's just see what's going on here. So as I said, like, let's suppose we fix the hidden units and then we want to update we fix the visible units and we want to update the hidden units. We want to look at the conditional probability of H given V. So that's the joint probability of V and H divided by the probability of V. And so really we don't have to worry too much about the probability of V because we're only allowed to change H. So we get this Boltzmann distribution based on that energy function. And so by following the similar kind of reasoning that we went through before, for each hidden weight, you just have to figure out that sigmoid of you have to figure out the sigmoid of the change in energy, right? So that's written here like this. We've got the sigmoid, and this is the weighted sum of the weights to that unit plus. This looks very busy, but this is like the weights from the visible units to that particular hidden unit plus the corresponding bias. and this is just saying that it's like a dot product with 2 times the hidden unit minus 1. And then this is, because remember, h is either 0 or 1, so this turns it into +1 or -1. Yeah, and then the same thing here. So if this is positive, then it's if this is positive, then this is more likely to change to +1 and vice otherwise to 0. And then once we've changed the hidden units, then we turn around and based on the hidden units, find the next value for the visible units. Yeah. So yeah, this symbol here is component-wise multiplication, and this is the sigmoid that we're used to. Okay, now how do we, and we want to change the weights so that these probabilities, the probability of the data that we've been given is maximized, and so we could do this by a process known as alternating Gibbs sampling. So we randomly start with an image. Yeah, again, it sort of goes, so let's go back and have another look at this video. Not the icing model, but it's funny. There was another video with the, here it is here. So let me just search again. Because you'll be able to see the hidden units here. Okay, so this is the early epochs of training. So up in the corner here, this is the image that it's being trained on. Right, so it's presented with an image. The image is fed to the hidden units and then comes back again, and we get this image. So we go from the visible to the hidden, and then from the hidden back to the visible. And in the early days of training, the image that we get back is just kind of a mess, right? Because these weights are pretty much random. So that's the hidden unit activations. The dots are 1 and the black ones are 0. And then the training is done by contrastive training. So this is a real image, and this is an image that's been kind of generated by the model, and so we assume that this is a fake, we assume that this is a wrong image, right? So we try to train the network to increase the probability of this image and decrease the probability of that image. And the training kind of goes on, and as we get into a little bit more training, you see, well, first of all, you notice the hidden unit weights are more evenly distributed. There's a larger number of them are 1s. There's sort of a more equal distribution of 1s and 0s. But you also notice the reconstructed image is looking a little bit better. Not fantastic, but better than it did before. And as the training continues, gradually these fake images get a little bit closer to the original images, but all the time we're training to decrease the probability of the generated images and increase the probability of the real images. And so on. And then there's another video we'll look at in a minute, which is the later stages of training. So just this is the real image. It's gone back and forth perhaps a few times to produce this image, and then that's the hidden units. So where's my... Right, so what's going on here? Well, this is the real image. I've got this set of 50,000 real images. I just pick one of them at random. That's my initial state. So this is the visible units. And then, well, in the original version of this algorithm, I do this several times. So based on those visible units, I make a select, I set the hidden units, and then based on the hidden units, I go back to the visible units. And I may go back and forth several times. And then after some number of steps, this should be an image which is representative of the probability distribution defined by this network. And this is the thing that we train negatively. Right, so this is the contrastive divergence, right? So we select one or more positive examples. Well, when I say one or more, this is to take advantage of the parallelism. So for each real image, we sample from the real vectors, we sample a hidden vector according to that probability distribution, and then we go from the fake back to the real, and back and forth, real, fake, real. We go from the hidden back to the visible, and then hidden, visible, hidden, visible, hidden, visible. If we did that a few times, we can get something that we can regard as like from the probability distribution favored by the network, and then we consider that to be wrong, right? So, and then we want to reduce that probability. And if you actually kind of go through the math, this reduces to some fairly simple linear equations. Yeah, so we want to increase the probability of the real image and its corresponding hidden units, and we want to decrease the probability of the fake image and its corresponding hidden units. And so we end up, it turns out that with the gradient descent, you do that by adding, for each pixel, you look at if there's a difference between the real image and the fake image, and you multiply by the learning rate, and you add that to the bias, and the same thing with the hidden units. And then with this weight here, you look at the Wi Hj minus Wi tilde Hj tilde. So this is just kind of simple linear calculus to increase or decrease, increase this probability and decrease that probability. Now, this took a long time to train, so then someone in Hinton's lab kind of had the idea, well, theoretically, we should be doing this process several times, but what would happen if we just do it once or twice? Let's say we start with a real image, generate hidden units, go back to visible and generate hidden units again, and we'll just take this pair as our, we'll just try to increase the probability of this pair and decrease the probability of this pair. And this is what's called quick contrastive divergence. And it was found that this actually gives pretty reasonable results. So these first two things are used as the positive example, the next ones are used as the negative example. And I kind of like to compare this with negative sampling and word2vec. If you go right back when we had word2vec, we had an actual, there were 60,000 words to choose from. We trained to increase the probability of the word that actually occurred. Theoretically, we should have trained to decrease the probability of all the 60,000 other words, but that takes a lot of computation, so instead we just chose a random sample of 10 or 12 words and decreased their probability instead of the whole 60,000. This is a similar idea. We're actually just taking, theoretically we should be running this back and forth several times. Well, you can think about it geometrically. You know, you start with a real sample, and then if you ran the back and forth several times, you'd get to another sample that may be quite far away, and you should be decreasing that and increasing this. Here, we're just picking a sample that's, because we're only doing this step once, we only have the opportunity to move a small distance away from the original one. So we're training to increase the probability of the real digit, and then we're training just to decrease the probability of another one which is quite close by. So theoretically, this could fail. You know, theoretically it runs the risk that you're only reducing the probability of the nearby things, and it could happen that things that are far away actually become more likely. That could happen in theory, but it turns out that in practice this gives pretty reasonable results. Okay, so let's just go back and see if I can find this this other video. Might have to just search late epochs. So this is the same run but further along. So you can see, because it's trained for quite a while, these reconstructed images are better, and you can see that they're close. I think this is probably the quick contrastive divergence. So they're quite similar to the original image, right? But then what they're doing in this part, they're saying, okay, well, they're not training the network, they're just allowing this Gibbs sampling to run many, many iterations to see what kind of fantasy digits get produced, and you can kind of see the way you move around through the space. So you sort of, at each time step, you're just changing to something that maybe is only a little bit different from the previous, but if you ran it for a long time, you would see a variety of different digits being produced, and the thing there is the hidden. So you can see the visible units and the hidden units. And yeah, so it goes on. Okay, any questions about this? Okay. Then you can have a deep Boltzmann machine. So this was kind of again, this work in a way is kind of outdated or superseded, but this was what was going on in Toronto in the period around 2008 or so, the early 2000s. So you would use a restricted Boltzmann machine. So the thing on the left is the restricted Boltzmann machine where you have the visible and the hidden units. Then you can add another hidden layer, and you can repeat the process here and try to reproduce the distribution of these hidden units with another hidden layer and another hidden layer. And there are some videos where you can see this happening with the MNIST. The idea is that the features should get more and more abstract as you go to the higher layers. You know, these features should be a bit more abstracted than those features. So there's some videos that go through this, and one use that this was put to was deep layer-wise pre-training. So this was one of the this was one solution to the problem of vanishing and exploding gradients. So if you go back to the early lectures, I talked about vanishing and exploding gradients, and I talked about batch normalization and weight initialization and activation functions. And I think I did mention at the time that layer-wise pre-training was another method. Well, this is what it actually is. The idea here is you train all of this unsupervised, so you train this, and then you train this, and then you train this. Then you've got a 3-layer network, and afterwards you can put it on an output layer, and you could train the network to do classification, and you get a better result than if you had just trained the whole network from the beginning, from random weights. Right? So this was thought to be important in that era, and there was a couple of variants of this algorithm, but what happened afterwards is that, people found afterwards that there are ways to train by backpropagation. There are ways to train a deep network directly without going through this process. You know, so the batch normalization made a difference. The weight initialization made a difference. Switching to the activation function made a difference, right? They switched from these guys in Montreal switched from the tan they switched from this sigmoid function to the ReLUs. You know, the ReLU is like equal to 0 and then equal to x. It turns out if you kind of throw all of that together, you can train a deep, and then there was the residual networks and the dense networks. So if you use those techniques, you can just train the thing directly. You don't have to do this unsupervised pre-training. So these methods aren't used that much these days, but it's interesting from a historical point of view. And the thing I mentioned, because these values are between 0 and 1, if you go through this process with a Boltzmann machine, when you do get to the final stage of training the whole thing by backpropagation, you would be using the sigmoid function. Right, so in the pre-training, those hidden nodes have to be either 0 or 1. They have to be discrete, but in the final stage, they are allowed to be continuous, and the activation function is the sigmoid. Good. Any questions about this? Good. Okay, we've still got 40 minutes left, so I am going to start another topic. It's a related topic, which is autoencoders. And it's related in a couple of different ways. This is another form of unsupervised learning, and this can also be used for unsupervised pre-training, among other things. And generative models. Okay, so all right, so we talked before about these encoder networks. So we looked at this in a very simple situation just to try to help get an understanding of the geometry of hidden unit space. we had this task where you had perhaps 5 inputs and maybe either 2 or 3 hidden nodes and then 5 outputs, and we had a one-hot encoding. And the task was just to get the output to reproduce the input, but there was a bottleneck in the middle. The number of hidden nodes was smaller, so the network was forced to do some kind of compression in order to achieve the task, right? So, I mean, people sometimes complain, well, that's just a toy model, it's not of any use. That's true, but it is possible to use the same principles in a serious model. So let's say we have images, and it's called an autoencoder. So we have a set of images, and we have a network that, if it's images, it'll be a convolutional network. So we have some layers, and we go through a smaller number of hidden nodes, and then we always try to reproduce the original image. So we put in an image, and we try to reproduce the image, and it's unsupervised. It's unsupervised because we're not giving it any classification labels or anything like that. There's no target values, we're just giving it the original images, nothing else. That's why we call it unsupervised. But the idea here is that by learning this to reproduce the input, it will somehow extract out useful features, and then those features can be used for other tasks. Okay? So we have an input, and hidden layer, and an output. So we call this an encoder, and we call this a decoder. So if we start out with X, and the encoder produces Z, which is f of X, and then the decoder is G of Z, then we're trying to train the output to be as close as possible to the input, so we're trying to reduce the distance between X and G of f of X, right? And often we use the sum squared error. Yeah, so if it's an image, it'll be just for each pixel you look at and each color you look at the 2 values in the input and the output, and the square, and that's the square of the difference, that's what you try to minimize. And as I mentioned, one of the purposes of this, not the only purpose, but one purpose is as unsupervised pre-training. So you can imagine, here I've just drawn one layer, but the encoder could have multiple layers. And so you could train this thing as an autoencoder, and then when you've finished the training, you can chop off the top part of the network, and then you could add on a layer that tries to do classification. You know, I could chop this off and add another layer that does softmax classification. And again, the idea is that if I do this unsupervised pre-training first, and then train it on the supervised task, it should give a better result than just training the thing from random weights in the beginning, because it should have already learned useful features. That's one purpose. I'll talk about other purposes. Okay, now I said that there's a bottleneck in here. Now it depends. So sometimes there is actually literally fewer nodes, but with these convolutional networks, we looked at these several different types of convolutional network for these image processing tasks. You'll notice they often had quite a lot of nodes in the hidden layer and quite a lot of weights. Sometimes they had millions of weights. Sometimes they had several channels in the hidden layer. So you could often have a situation where the number of nodes in the hidden layer is actually larger than the input. So there's this kind of risk with that kind of model that what we really wanted to do, we want to have some kind of compression because we wanted to actually learn features that are specific to that style of image. There's a risk the network might just learn the kind of identity function that would reproduce any image, and that would kind of defeat the purpose, right? So in order to avoid that, we often introduce some form of regularization. And these are discussed in the textbook in section 14.2, so I'll go through some of these. So the sparse autoencoders with dropout at the hidden layers, contractive autoencoders and denoising autoencoders. So so the second one, the autoencoders with dropout at the hidden layers. I don't have a slide about that, but we talked about this before. We talked about dropout. So if you have the hidden layers and you randomly drop out some of the connections or even some of the nodes, that's one way of regularizing because it forces the network to be able to do the whole job with fewer nodes. Right? Now the sparse autoencoder, you add a penalty term in the loss function based on the hidden unit activations. So we try to keep this is analogous to the weight decay term we previously used for supervised learning, but instead of trying to keep the weights small, we're trying to keep the values of the hidden units small. And most commonly we do, this can be done with, we can try to reduce the sum of the squares of the hidden unit activations, or we can try to do it with the sum of the absolute values of the hidden unit activations. It turns out for this task, you get a bit of a better result if you use the absolute values rather than the squares. So this is, if we use the absolute values, it's called the L1 regularization. If it's with the squares, we call it the L2 regularization because the thing is squared, whereas with the absolute value, it's raised to the power 1 in some sense. And what happens with this L1 regularization is it achieves this by encouraging some of the hidden unit vectors to kind of go to 0. And so it ends up producing what's called a sparse representation often, where some of these values go to 0 and then the others have to be used to reconstruct the image. And this would particularly be true if you're using ReLUs. With ReLUs, it's easy for some of the activations to become 0 if you're using ReLUs. Easier. And then there's the contractive autoencoder. Now, what this does is the penalty term applies to the L2 norm of the derivatives of the hidden units with respect to the inputs. So the PyTorch the autograd calculates gradients of the hidden units based on the inputs, and we can actually apply a penalty term to those gradients, right? So this grad x of hi is the gradient of each hidden unit with respect to changes in the input, and we can calculate the norm of that, and we can try to penalize if that gets too large. We add that as a penalty term with some lambda, and what this does is it forces the net model to learn hidden features that don't change much when the inputs are slightly altered. So this is, I'll maybe say a bit more about this next week, but these deep networks can be fooled. There's examples where you train a network on ImageNet and you have an image of a dog, and if you know the structure of the network, you can make very slight changes to the image that aren't perceptible to a human, but suddenly the network thinks that it's an ostrich instead of a dog, you know, or things like this. So minimizing this is that's part of the motivation for this kind of thing. But it's also gives a better result for these autoencoders. And finally, we have what's called the denoising autoencoder. Well, not finally, because we'll get to the variational autoencoder. But the denoising autoencoder, it's a similar idea, but what happens here is you start with an image and then you corrupt the image by adding some noise. You add some Gaussian values to the noise as if it was like on a fuzzy television screen or something. But then the autoencoder tries to reconstruct not the fuzzy version but the original image. The task of the autoencoder is it's given the corrupted image and it tries to produce the original image. Right? So you sample an image, the corrupted version is x tilde, and then it's trying to reduce the distance between x, the original image, and g of f of x tilde. Okay, so these are just different forms of regularization. Okay, so, but then this leads on to the variational autoencoder. All right, so, but how do we need a bit of theory to get there. Okay, so the loss function can be seen as a probability. So we saw this with the classification. The softmax function, we interpreted the outputs as defining a probability distribution over the outputs. So for these autoencoders, if we change the parameters theta in the network, then it can be seen as like changing the probability distribution over the outputs. And each network that we've looked at relates to a particular kind of probability distribution. So we saw how the squared error is based on the assumption of an underlying Gaussian distribution in the noise. And the cross entropy was based on what's called a Bernoulli distribution. A Bernoulli distribution is just a fancy way of saying that the value of 0.8 means an 80% chance of 1 and a 20% chance of 0. That's called a Bernoulli distribution. And the softmax assumes a Boltzmann distribution. So we've seen already examples of these three different distributions. Now for an autoencoder, often it's useful to use different symbols for the weights of the encoder and the decoder. So if the encoder is, if the decoder is P, then we feed in these hidden variables Z and it produces an image X, and the weights are theta, so this actually kind of can be thought of as defining a probability distribution over images based on the latent variables. And the encoder can perhaps also be seen as a probability distribution of the latent variables based on the images. And we write this as Q's of Z depending on X. And this relates back to what we were just looking at with the restricted Boltzmann machines. We're using different letters here. So with the Boltzmann machine, we used V for visible instead of X, and we used H for hidden instead of Z. But what was going on here was exactly this, that the Boltzmann machine, it defines a probability distribution if I give you an X, it defines a probability distribution. If I give you the visible units, it defines a probability distribution in the hidden units and vice versa. So these can be thought of as an encoder and a decoder. Now, in the case of the restricted Boltzmann machine, it was restricted in the, well, because these weights are symmetric, the probability distribution, the same weights are determining both of these conditional probabilities. But in general, with encoders and decoders, we can have different architectures and different weights, but we still have these sort of conditional probability distributions. Okay, and so this is where we get to generative models. So remember what I said about the Hopfield network and the Boltzmann machine. So the Hopfield network was just trying to reconstruct the original images. The Boltzmann machine was intended to generate new images. We have the same issue here, that the autoencoders that we've discussed so far are mainly intended to just reconstruct the original image. But if we make slight changes, maybe we can use this kind of model to also generate new images. Right? So let's say, just to go back to this, let's suppose I've trained an autoencoder. Then theoretically, if I throw away the encoder and just keep the decoder, if I put in if I just choose random values for those hidden units, then it should be able to produce an image, and maybe it will be a realistic looking image. This is the idea. I'll talk next week. We'll look in more detail at the architectures of this, but normally the encoder, you have some convolutional layers and then you have some fully connected layers, and then the decoder, you go from the fully connected layers and then some convolutional layers. So these hidden units don't have any explicit geometry about them. It's just, a bunch of sort of fully connected activations, So if we were going to do this, so then the question becomes, well, if I want to choose random values for these hidden units, from what probability distribution should I choose them? And normally the answer is a Gaussian distribution. So let's suppose that there's 100 hidden units here. So I take an image, I apply my encoder, and it gives me 100 numbers. And then the decoder is taking those 100 numbers and is producing an image. So those 100 numbers are supposed to represent the image in some sense. So if I want to generate a random image, for each of those 100 numbers, I choose a random number from a Gaussian distribution, right? So a normal distribution, a normal bell-shaped distribution with a mean of 0 and a standard deviation of 1. And I'd like it so that when I choose those variables randomly, it produces a realistic image. That's basically what I've said here. Yeah, we want to be able to choose latent variable z from a standard normal distribution. A standard normal distribution means there's a Gaussian distribution, mean of 0 and standard deviation of 1 in every component. I want to be able to feed those values in and get back an image which looks realistic. And this is called a generative model. Now, today I'm going to talk about variational autoencoders, and then next week we'll talk about generative adversarial networks, which do the same job. Now, this variational autoencoder is called an explicit model because there's like a well-defined probability distribution, and it's based on the original images. The generative adversarial networks are called implicit because there isn't any explicit probability distribution in there. I'll say a bit more about this next time. Okay, I think I thought I had updated this. These slides, I thought I had taken these slides out. They're just repeats of earlier slides. But anyway, I think I need to upload. There's a slight revision to these slides I intended to upload, but maybe didn't quite get updated. But anyway, this variational autoencoder makes use of this KL divergence. Well, how should I put this? Okay, so let's think about this autoencoder. The problem is, okay, so I want to be able to choose latent variables from my Gaussian distribution and have them lead to realistic images. But the problem is that when I train my autoencoder, the original images might not get mapped to that Gaussian distribution. The original images might get mapped to some other distribution. There might be some latent variables that aren't really used at all. I provide 100 nodes, but maybe it really only uses 50 of them. Or all the original images get mapped to a subspace. So in that case, if all the original images get mapped just to some very small subspace, and then I randomly choose something that's outside of that subspace, then it may produce an image that looks very unrealistic. So you may have a situation where it reproduces the original images faithfully, but when I choose a random variable here, it produces a really stupid looking image. And so in order to avoid that, we want to have a mechanism in there which tries to force the original images to get mapped to the Gaussian. We want to force the original images to kind of spread out, not bunch up in a small space, but spread out and cover the entire Gaussian distribution. So this is a sort of picture of this is a picture here of what the hidden unit space might look like if we train on those MNIST digits. This is, each color represents a different digit. So all the zeros have been mapped here, and these are the ones and the twos and the threes and so on, and this has been projected from 3 dimensions down to 2 dimensions, but this is what we want to happen. The original images have nicely spread out to cover the whole space, and you can kind of imagine that if we choose something from a Gaussian distribution, very likely we'll be choosing something that's close to an original image. There are some gaps. If we choose something here that's a little bit away from the original images, we would get something that's sort of a cross between a 0 and an 8 or a 0 and a 7. It might look a little bit kind of, or a 0 and a 1. So if we choose something in here, we might get something that looks a little bit weird. But if we choose randomly from a Gaussian distribution, it's kind of evenly spaced around this ball, and we can expect there's good coverage of it. And this is actually some of the reconstructed images. Yeah, you can see how it morphs. These are the 1s, these are the 7s, these are the 0s. and you get these sort of little boundary things that look like a little bit of a cross between two different types of digit. So that's what we want to achieve. Now, how is that achieved? Well, this is where we go back to this KL divergence that we talked about earlier on. The KL divergence gives us a way of measuring how close one probability distribution is to another. And so the way this model works is the encoder, instead of just producing, this is, I'll go over these details next week because I could see we're reaching saturation, but let me just briefly say what's going on. So the encoder produces a mean and a standard deviation. And so instead of just producing a single value, you put in an image, and you have two sets of hidden units. One set of hidden units produces the mean, and the other set of hidden units produces a standard deviation for that latent variable. And then the decoder, when you apply the decoder, you sample from that mean and standard deviation. So the encoder is saying, okay, for this particular image, instead of just, it's in the original autoencoder, it says, okay, for this particular image, the value of latent variable 1 should be 0.65, and the value of latent variable 2 should be minus 0.32, and so on. Now it's saying, it's actually giving you a range. It's saying, okay, well, it should be 0.65, but you're allowed to change it by plus or minus 0.15, and that'll be safe. It won't change the image too much. On the second variable, it should be minus 0.35, but you're only allowed to change it by a smaller amount, 0.08 or whatever. So for every coordinate, it gives you a mean, and then it tells you like how much you're allowed to change it by. And the decoder says, okay, well, I'll add a little bit of random noise based on that standard deviation, and I'll feed that into the decoder and try to reproduce the original image. So this is explicitly telling you, it's a little bit like the denoising autoencoder, except we're adding noise at the hidden units, not at the input. And the network's actually telling you how much noise you're allowed to add and still be able to reproduce the original image. So it kind of like, it's sort of like having a little balloon. For each input image, you have a little balloon, and it specifies the size of the balloon. And then we add something to the loss function to try to make those balloons like expand and cover the whole space. So the way we do that is using the KL divergence between the balloon and the standard Gaussian distribution. So this is actually how it works. This first term here is the the reconstruction error. If we start with an image xi, the encoder determines this little probability distribution. We choose Z from the probability distribution, feed it to the decoder, and we should get something that, with high probability, it should reproduce the original image. So that's the first term, is trying to maximize the likelihood of reproducing the original image. And this second term tries to minimize the KL divergence between that small balloon and the entire Gaussian distribution. So it encourages each balloon to try to well, it encourages the mean to not get too far away from 0, and it encourages the standard deviation to increase as much as possible. So there's this tension. This term is trying to get these standard deviations to increase, but if they increase so much that the original image isn't reconstructed faithfully, then this term will suffer. So there's this tension between these two terms, and somehow there's something a little bit strange about this, because, like I said, you could think of each point here as a little balloon, and that loss function is trying to get each balloon individually is trying to approximate the whole distribution, which obviously they wouldn't be able to do. But in practice, the balloons expand, and between them, they end up covering the whole distribution, right? So this is called the variational autoencoder. And this is the kind of results that we get from the variational encoder. It's better than what we got with the Boltzmann machine, but it's a little bit fuzzy. So these are the original digits. After 9 epochs of training, so this is, each digit here is meant to be a reconstruction of the corresponding digit here. They're pretty reasonable, but they're a bit fuzzy. And you can use this for faces as well, and the same thing again. They do actually look pretty realistic, but there's a little bit of a fuzziness there. And so yeah, it produces reasonable results. The images tend to be a bit blurry, and you still get this, in spite of our best efforts, you still see this phenomenon that often it ends up using only a subset of the dimensions that are available. So it's, if you make 100 dimensions available, it may end up that all the original images are actually getting mapped into a smaller number of dimensions. Yeah, so it doesn't fully solve this problem, but it's better than just a standard autoencoder without variation. Okay, so I think so next week I'll talk mainly about generative adversarial networks. So this is a way, it sort of does the same kind of job as a variational autoencoder, but it produces better images. And the basic idea is you have the generator network, and then you have another neural network. You feed the images from the generator into another neural network, and the second network is trying to tell which of the images are real and which are fake. So you actually are using another network to try to force you to produce more realistic looking images. Okay, any final questions? Good, okay, I'll see you next week. Well, it allows, how should I put this? Yeah, it's a little bit, See the energy function. For the energy function, the energy function is a particular form, right? So the probability of each unit has to be a linear.